In this video, we are going to talk about section 8.4 on trig substitution. So this is a new method for doing antiderivatives. Our goals are to recognize when and how we use trig substitution. So in this video, we will look at an example to introduce what trig substitution is. And I want to begin with a warm-up problem where we have to evaluate the integral of x over the square root of 1 minus x squared. So we're going to practice doing this using our previous methods. So I want to have you pause the video and try this for 2 minutes. So pause it in 3, 2, 1, pause it and try it. Okay, so hopefully you did that. Hopefully you paused it and tried it. We can do this with a u sub. We can let u be 1 minus x squared, because then du is negative 2x dx. And at this point, I can recognize that this is going to work because du, ignoring this constant multiple, ignoring that negative 2, I see this function x in my integral. I see it here in the numerator. That's an indicator that this is going to work. So if we rearrange this, we get du over negative 2 equals x dx. And now we can sub in, because x dx, I see that that's now just du over negative 2. So replacing that, we get a du over negative 2. That's going to get multiplied by a 1 over square root of u. And now this is much easier to do the antiderivative of. I can pull the negative 1/2 in front. Integral, that square root of u on the bottom becomes a u to the negative 1/2 du. Now I can do reverse power rule on this. So I keep that negative 1/2 in front. So I add 1 to the power to get a u to the 1/2. And normally I would divide by 1/2, but that's the same thing as multiplying by a 2 in front. This is an indefinite integral, so I got to put my plus c. And then the 2's cancel, and I get negative. This becomes a big old square root. We plug back in for u to get a 1 minus x squared, and then I get a plus c. Okay, and that's my answer. Okay, so now I want to turn our attention to another example, but where I'm changing the numerator from x to an x squared. And it turns out that when we do that, now this same u sub, which was giving me du, just giving me this function x, ignoring this minus 2, this constant multiple, well, I don't just see x in this new function, because I see x squared on the numerator. And it turns out that that difference is going to prevent this u sub from really being helpful. It turns out that none of our previous methods really help us on this. So how can we do this? When I look at this denominator, I see something that looks like the square root of 1 minus some stuff squared. And we've seen things that look like that when we do the Pythagorean theorem. So when we do the Pythagorean theorem, which says a squared plus b squared equals c squared, if we isolate the b squared, we would get b, and let's also square root both sides. I'd get c squared minus a squared. Then I would square root. Ordinarily, when I square root both sides, I need to put a plus or minus, but I don't need that here because b is a length, and a length can't be negative. So the fact that this denominator term reminds me of the types of things that we might get from a Pythagorean theorem, in this case, this is where the c would be 1, it makes me think let's use a right triangle like we have with Pythagorean theorem. So let's draw a right triangle. I'm going to draw a right triangle. And this side, the square root of 1 minus x squared, it kind of looks like this, which we are calling b. So I'm going to let this be one of the legs. And it doesn't really matter which one I pick. We can make it work either way. I'll just make it be the vertical one. And now I'd like to know what the other two sides are going to be. So to do that, we can use our Pythagorean theorem. I need to know what these other two sides are going to be. So, well, if I do this square root getting squared, it gets rid of the square root, and we have this. And now let's think of what can fill in these two parentheses so that both sides of this equation are going to be exactly the same. I want to have you pause the video for 30 seconds and see if you can figure out what goes in those parentheses. So pause it in 3, 2, 1, pause it. Okay, so let's talk about it. There's many possible things that we could use, but the simplest is maybe to pick an x here, because then this x squared and that minus x squared will cancel, and then a 1 would go in that parentheses. Okay, so a 1 in the other parentheses. Okay, so the other leg is x, and the hypotenuse is 1. Now I'm going to label one of the angles to be theta, and it doesn't matter whether I let it be that one up top or the one on the bottom. We can make it work either way. So maybe I'll just put theta here on the bottom. So that's my first step, set up this right triangle. Then we want to set up trig expressions for the parts of the integral. So on the denominator, for example, I see this square root of 1 minus x squared. And in my triangle, I see a square root of 1 minus x squared over here. So that's the opposite side. So for example, if I do sine of theta, sine is the opposite over hypotenuse. So square root of 1 minus x squared all over 1, which is just the square root of 1 minus x squared. Okay, so I'm going to highlight that in green. That square root is just sine of theta, which means I'm going to be able to replace that denominator with sine of theta. Okay, so I still got this thing on the numerator, x squared. But I see x in my triangle. So let's set up a trig function that will involve this side, the adjacent side. And there's multiple choices, like I can do tangent, which would be this opposite over the adjacent. Or I could do cosine, which will be this x over the hypotenuse. So which one should I pick? We typically want to pick the trig function that involves the side that we are trying to get. So we're trying to get something with an x. And then also another side that's a constant, if possible. Because if I pick something that involves this side, it's going to introduce an extra term with the variable, which I might not necessarily want. So because of that, let's set up cosine. Cosine will be x over 1, which is just x. So let's highlight for that. So this x squared, I'm going to be using the fact that, well, x is cosine, and then we can square both sides. Just like we do with the u sub, I'm also going to have to plug in for this dx. We can do that by taking the derivative of my substitution. Usually we do the derivative of the simplest one. And it looks simpler to do the derivative of x than to do the derivative of the square root of 1 minus x squared. So if I do the derivative of cosine, I'll get negative sine theta. I got to write a d theta next to it, kind of like I do with the u sub. Derivative x is 1, and then we write a dx next to it. Oh, and now I can see that dx is just negative sine theta d theta. So now we are going to be ready to substitute in. So substitute in. And if we do that, our integral becomes, in the numerator, we get cosine squared theta. Let's highlight that in orange. That denominator, that square root term, well, that just became sine of theta, right? That square root term was just sine of theta. And then finally, there's that dx at the end. And we just got dx. We put that in blue. Dx is negative sine theta d theta. Okay, awesome. So I can cancel the signs. I can pull the negative in front, and I get negative integral of cosine squared theta d theta. We saw how to do the antiderivative of cosine squared in our last section on trig integrals. We need a trig identity for this. This is 1 plus cosine of 2 theta all over 2. Okay, so now I'm dividing by 2, so I can pull that 2 that's on the denominator out in front of the integral. That'll give me a negative 1/2 in front times the integral. Oh, and actually, let's just start to do the antiderivative. Let's move that negative 1/2 in front. The antiderivative of 1 is just theta, because the variable's theta and not x. Antiderivative of cosine of 2 theta, well, that's going to be sine of 2 theta, and then something's going to be in front of it, because the derivative of sine of 2 theta involves chain rule. I would get cosine of 2 theta, but then I also do the derivative of the inside, which pops out a 2. But there's no 2 up here next to that cosine 2 theta. So to cancel out that 2, I would need to put a 1/2 in front of this. Okay. And then this is an indefinite integral, so I need a plus c. Okay, and I got my antiderivative. Just like with the u sub though, the original variable was x, and right now I have it in terms of theta, so I'm going to have to sub back in. So to do that, one of the things that I can do is I see I have this theta here. And to isolate for theta using my substitutions, we are going to need inverse functions. So I can pick either one, but maybe I'll pick cosine just because it looks simpler. So if I rearrange this with using cosine inverse, it swaps the input and the output. So I get cosine inverse of x equals theta. So we're swapping this input and that output. They're swapping spots. Okay, so now I know what theta is. So we got -1/2, big old bracket, theta ended up equaling cosine inverse of x. We could technically plug that in for this theta as well. It just turns out that when you have an inverse trig function inside of like an actual trig function, often that simplifies really nicely. But it's harder to tell how it simplifies by just kind of plugging it in right now. So how can we simplify this? So there's a trig identity for sine of 2 theta. So I got that 1/2 in front. So what is sine of 2 theta? So recall that sine of 2 theta is 2 sine theta cosine theta. Close that bracket, and then I got my plus c. Oh, and that's nice because I know sine of theta. It's just this square root term. And I know cosine theta. Cosine theta is just x. So I can plug those in. So I got that -1/2 in front, big old bracket, cosine inverse of x. The 2's cancel. Sine of theta is square root of 1 minus x squared. That'll multiply cosine of theta, which is x. But let me just put that in front of the square root. I just think that looks a little nicer. Close the bracket, and I got my plus c. And we got it. We got our answer. So we've just done our first trig sub problem. Okay, so typically when folks first learn this, often we might think, wow, trig sub's so long. Like there was so much involved in it. This triangle, setting up these equations, so I can do the derivative and plug in, and then I had to evaluate. There was trig identities even involved, which happens sometimes, but not all the times. As we get more practice with this, we will get faster with this. Okay, so let us flip the page. Let's state some of the takeaways from this. So the key indicator to try a trig sub is if none of our other methods works, and our integrand, which is the function we are trying to integrate, contains something like the square root of stuff minus x squared, or the square root of stuff plus x squared. So if I have this first one, or if they were switched, and I had the x squared first minus the stuff, that's kind of like the one we just had in our problem. Then we make this side be the leg of our right triangle. And that's what we did here. We had the square root of 1 minus x squared, and we made that be the leg of the right triangle. If instead we had the square root of stuff plus x squared, that could happen if instead we were isolating c, we would get the square root of this whole thing, something plus something. Then, because that's c, that's going to be the hypotenuse. You make that be the hypotenuse. And we'll see an example in a future video where that happens. So what I want to end this video now by talking about is, well, what if I had to do a trig substitution like this, but I had a definite integral? How do we handle that? So there's a couple ways we can end up plugging those in. And one of them, let's talk about one of those strategies. So if we have a definite integral and, because I did a substitution, I have to convert those x's to theta values. We have to restrict ourselves to intervals on which the trig function is 1-to-1, meaning it's got to pass the horizontal line test. I need that so that the inverse function would be defined. Like we were working with the inverse function here, kind of implicitly when we were plugging back in. Okay, so what if when I did my substitution, whatever x equaled ended up being a number times sine theta? Well, we've seen before that with, to make this thing be past the horizontal line test, there's many ways I can do that. Like I can pick an interval like this, or let me go to laser mode. I can pick an interval like this. there's many choices. So the convention is make the interval kind of as big as possible and have it be centered. So it turns out that is from negative pi over 2 up until pi over 2. Negative pi over 2 up until pi over 2. Okay. If my substitution was a number times cosine theta, if that's what x equaled, and that's what was happening here, x equaled cosine theta, well, the convention for this one is start at 0 and go up until pi. Ooh, let me draw that better. Start at 0 and then go up until pi. So from 0 up until pi. For tangent, the convention is use this middle piece. So use that middle piece. So then theta goes from negative pi over 2 up until pi over 2. There's no equal signs on these because there's vertical asymptotes at those angles. So we can't actually reach those angles. Secant is, I think, the most complex out of these in terms of this domain restriction. Because with secant, there's parts of the graph where the y values are positive, like this. But there's other parts where the y values are negative, like this. So if I try to pick an interval where it's positive, if I focus on a centered part, I could either pick this part on the right or this part on the left. But I can't pick both because then it wouldn't pass the horizontal line test. So the convention is, for the positive y values, we're going to pick this part on the right, which goes from when theta is greater than or equal to 0 up until pi over 2. No equal sign at the pi over 2 because there's an asymptote at pi over 2. But then there's also parts of the graph where the angle could be negative. And then the convention is to use, where the y values are negative. And the convention is we use this piece, but do I use the left or do I use the right? Technically, we could use either. The convention is maybe a little weird. Like we end up using this right piece. So that's when from theta is pi up until 3 pi over 2. The reason we use that right piece has to do with sometimes when we do these trig subs, we end up with things like the square root of tangent squared, which technically, if you square root something squared, is the absolute value of tangent. And if you pick your angle to be between pi and 3 pi over 2, this tangent is positive. And if it's positive, then when you do the absolute value, you can just drop the absolute value. So this is positive on the interval from pi to 3 pi over 2. So you could just drop the absolute value like that. But if instead we had used the interval from pi over 2 up until pi, well then tangent would have been negative. So when you drop the absolute value, you would have needed to put a negative in front of this, which is just a bit more complicated. Okay, so that's why this happens to be the convention for secant, for what the angle should be. Okay, so let's end with an example. I got the exact same function as before that we were doing our trig sub on, and now we have these limits of integration. So there's a couple ways to do that. The first way is we could, convert it all the way back in terms of the original variable, like we have, and now just plug in these two numbers. Plug in the 1/2, plug in the 0. There is one thing that's a little bit annoying for this problem with doing that, which is you'd have to plug them into a cosine inverse, and you'd have to simplify, like what's cosine inverse of 1/2? So we'd have to do a little bit of work to figure out what that is. The other way to do it is you could have stopped at this step when you have it just in terms of theta, and you can convert your x values to theta values. So let's practice doing that. Because sometimes we'll be given a problem straight like this, and if we're given straight like this, often it's quicker to kind of stop the trig sub at this point and now start plugging in. Okay, so I'm going to use that step where we had, what was it? It was a 1/2 or negative 1/2 in front. Negative 1/2 bracket theta plus 1/2 sine of 2 theta. Okay, and I'll put a vertical line because I'm going to have to plug in some values. But these are x values currently. I have to convert them to theta values. And just like with the u-sub, to do that, we plug into our substitution. So right now these are x values. We have x equals 0 and x equals 1/2. So the simpler out of these two, it looks like, is the one with cosine. So x is equal to cosine here. So I get cosine of theta equals 0 and cosine of theta equals 1/2. And here's where I got to use this angle restriction for cosine. I need the angle to be between 0 and pi. So cosine of what is 0? Well, on that domain restriction, it's just at pi over 2. And when is cosine 1/2? Well, it's just at pi over 3. Okay, nice. So this bottom number, the 0, converted to a pi over 2 in terms of theta, and the upper one converted to a pi over 3. This is a definite integral, so I don't need to put a plus c when doing this. Okay, so nice. So nice. Okay, so let us start to plug in. So I got negative 1/2. And then I'm going to plug in pi over 3. So I'll get pi over 3 plus 1/2 times sine of 2 pi over 3. All right, and then minus what I get when I plug in pi over 2. So I'll put a big old parentheses. Plug in pi over 2, I get pi over 2 plus 1/2 sine of pi. Okay, and then I'll close the bracket. Okay, so nice. So I can simplify this a little bit. Sine of 2 pi over 3, that just becomes root 3 over 2. Sine of pi just becomes 0, so that goes away. Okay, nice. From here, I can get some common denominators a little bit, like with pi over 3 and then minus pi over 2. I can multiply these two fractions, and then I can distribute this negative 1/2 into terms. I'm going to trust that we can do that common denominator and distributing in, and just tell you what we end up getting at the end once we do that. We'll get pi over 12, and then we'll get minus square root of 3 over 8. And that's my answer. It turns out that if we were to do this the other way, where we take these x values and plug them into the final answer that we had, that was completely in terms of x, I'd encourage you to do that. We should end up with the same thing. You know, we have to work out what cosine inverse of 0 is and cosine inverse of 1/2, which is, still takes a bit of work to do. So we could do it either way. Okay, and there we have it. So in the later videos in this section, we are going to do more trig sub examples. And in particular, we'll talk about how do we recognize when to do trig sub and when not to.